Hello everyone and welcome back to another video on the FODS YouTube channel. Today we're going to be doing a very nice electrostatics problem from the physics cup, but before we get into it, I'm going to do some shameless self-promotion. I actually run a separate YouTube channel called Slipping Hexagons, and if you guys could check it out and leave a sub, I'd really appreciate it. Alright, so now for the problem. This is Physics Cup 2012-6, and if you don't know, the Physics Cup is a competition run by our very own Jan Calda. And it is sort of the Putnam of the physics world, and the Putnam, of course, is an incredibly difficult undergraduate exam for math. However, this particular problem actually was proposed by an author of 200 Puzzling Physics Problems, Goila Hoynick, but I probably butchered the name there, and it's pretty interesting. The physics world is not that big, but anyways, let's get straight into the problem. So there is a solid metal sphere of radius r which is cut into two parts along a plane in such a way that the outer surface of the small part of the sphere is pi r squared. The cut surfaces are coated with a negligibly thin insulating layer, and the two parts are put together so that the original shape of the sphere is restored. Initially, the sphere is electrically neutral. Then, the smaller part of the sphere is given a small positive electric charge plus Q. The larger part of the sphere remains neutral. Find A, the charge distribution along the sphere, and B, the electrostatic force between the two pieces of the sphere, and C, the electrostatic energy of the sphere. Alright, so let's get started with 1, which is sort of the base to all this entire problem. And the idea behind 1 is just guessing and finding a charge distribution that works, and it will be guaranteed by the uniqueness theorem, which states that for a given charge distribution, then the potentials are uniquely defined. So we draw. Instead of using these 3D pictures, it's probably much nicer if we have a 2D picture so that it's not all messy, because this is, while it looks clean, it's going to be messy if you start drawing on it. Oops. Let me change my size there, but so we have a circle. We have a circle here, which is the sphere, and let's say that it is divided here. Actually, I'll put it solid since it's an actual division, and the surface area on this side is pi r squared, and of course this is going to be 4 minus 1, which is 3 pi r squared, as given in the photo. And so these are conducting spheres, or metal spheres, so it's assumed to be conducting. So one of the conditions we need to satisfy here is that the inside of this sphere is electrically has no electric field. And one guess we could do is say, oh, why don't we uniformly distribute charge around the outside? Because, sorry, those aren't pluses, but why don't we do that? So that could be our first possible guess. This is sort of like if you've done image charges, which I believe is a video on this channel, where you just kind of guess until you find a solution that works, and then it's guaranteed by the uniqueness theorem. So if we uniformly distribute positive charge around the outside like that, since of course we added plus Q, if we do that, then of course the charge on the inside being 0 is going to be satisfied, and that's great. But the only issue here is that there's going to be actual extra charge lingering here, because there's an insulating layer, which means that this side, which had Q equals 0, is going to remain electrically neutral. So there's going to be some negative charge if we just do this. So the way we can fix that is we can make all the negative charge distribute uniformly on this side, and then add some positive charge here. And the reason we add some positive charge there, and so the reason we need to add this positive charge is so that with a uniform distribution on the outside, and this stuff won't affect the actual electric field within the spheres, since these two are just like, if you know capacitors, if you have two parallel plates, electric field is only going to be between these, of course ignoring fringe fields. And so if we uniformly distribute charge here on this surface here, which is the surface I'm talking about, and we uniformly distribute charge on the actual outside of the sphere, then the electric field on the inside is going to be inside of these conductors is going to be 0, and this is actually going to be the charge distribution because it works. So now we know qualitatively what the charge distribution is, and this is guaranteed by the uniqueness theorem. So from here, let's try to do it a bit more quantitatively. So let's say the charge on this inner portion here is Q. Then, since by symmetry, as I stated earlier, D should have no effect on the outside in order to ensure a zero electric field, so the charge here should be negative Q. And then this bottom portion, since it's insulating, should have a charge of Q, positive, just like this one, in order to keep this inside electrically neutral. And lastly, this outside is going to be Q minus Q, to keep this one have a total, to make sure that this one has a total charge of plus Q. So from here, we wanted uniform distributions on the outside as well. So the way we can ensure that is we let the surface charge density of the top part, which is Q minus Q over pi r squared, and set it equal to Q over 3 times pi r squared. So the pi r squareds cancel. We have 3Q minus 3 little q equals Q, which implies that Q is equal to 3/4 Q. So instead of plus Q, oops, I'm not going to erase that, we have 3Q over 4 here, and we're going to have Q over 4 here, we're going to have 3Q over 4 here, and negative 3Q over 4 here. So that's our charge distribution right here. We have uniform charge distribution with total charge 3Q over 4 on the top flat face of this hemisphere, and we have a uniform charge distribution on the outside of the total sphere with total charge plus Q, and negative 3Q over 4 on the bottom side of the flat face, bottom side flat face. So now we know the charge distribution quantitatively, and this answers part A. And from here, we can, not pretty easily, but we can get part B. So part B, the way we're going to do it is, let's just focus on one sphere since the force either way is going to be the same by Newton's third law. And let's look at the force on this little top piece. So the way we can break it up into just the charges on the top and the flat piece at the bottom. And the reason we can just break it up, well, this might be obvious to you, but when I did it, it wasn't actually that obvious. When you break it up, of course, if you consider the total force on here, there's going to be some force due to this charge here, and you might be like, oh wait, that's an internal force, we have to cancel that, but of course that's going to cancel out either way, since the same force is going to be opposite on this one. But, well, it sounds pretty obvious now, I guess, but let's focus on this one since it's probably easier. So for this one, we already said it's in a uniform charge distribution on the outside. I guess that's a bit cut off, but uniform charge distribution on the outside. And that means there's no electric field due to all these charges, so the only electric field in this region is going to be the force due to this uniform charge here. And there's one idea that with a sheet of charge, you take the average between the electric field on one side and the average on the electric field on the other side. But for capacitor plates, we can actually just think of it as the force due to the electric field from this bottom part. So let's let this plate have charge density sigma sub 1. Then the electric field from the bottom, which has charge negative sigma sub 1, is going to just be negative sigma sub 1 over 2 epsilon naught. This is a pretty well-known fact, and you can just see this by considering this Gaussian pillbox here, and also ignoring this, because otherwise you'd have zero electric field here. So that's the electric field on this plate. So we know the force per area is just going to be multiplying the charge density here, and then we want to multiply by the total area. So we actually want to find the total area of this part here. So for that, we're just going to use a little bit of calculus here. So we have some hemispherical shell, and we want to find, that's a bit tilted, but I guess I'll just draw the rest tilted. And we want to find the area at the bottom here. And so the way we're going to do that is just to find this angle here. And if you know the angle, we know the radius, and it's a circle, so we can just find the area. So we have to find the surface area in terms of this angle, the surface area of the actual cap. And the way we're going to do that is just a double integral with spherical coordinates, with just the angle coordinates. And so the area component, if you just draw it out here, if I can, this area component is going to be r squared sine, I know I use theta here, but normally that's a phi in spherical coordinates, sine phi d theta. And I'm not going to really have time to go over why that is, but you can just draw it out and consider the infinitesimals. And if this is uncomfortable for you, you can just break it up into rings and use single variable calculus, which of course is actually just the same calculations. This one just looks complicated. Actually, it looks more complicated, but it looks simpler to someone that is familiar with it. So the inside is going to be 0 to 2 pi. I should have switched to d phi and d theta, but whatever. And this one is going to be from 0 to theta. So this is just going to be 2 pi r squared times 1 minus cosine theta. And since we said the spherical cap has area pi r squared as given in the problem, that implies that cosine theta equals 1/2, and so theta is equal to pi over 3. So if it's equal to pi over 3, this radius here, which is still tilted, sorry about that, is going to be r sine theta, which is equal to root 3 over 2r. So the area of this is just going to be 3/4 pi r squared. So it's going to be, so the force, let me move over to the side, the force, which I'll call F sub 1, is equal to negative sigma sub 1 squared over 2 epsilon naught times area. And we know area is 3/4 pi r squared, but before plugging that in, I can actually cancel that with a sigma sub 1. And that'll just give the total charge, which is 3q over 4. 3q over 4. And we're dividing by 2 epsilon naught. And so now we can plug in area here. And it's going to be 3q over 4 squared. Negative. And we're dividing by 2 epsilon naught times the area, which is 3 pi r squared over 4. So then the 3/4 is going to cancel, and this is equal to negative 3q squared over 8 epsilon naught divided by r squared times, and we have to leave the pi in there. So this is going to be the force of attraction between these two plates, and the negative is there because the force is attractive. So now we have to find the force to the hemispherical shell, and we don't have a lot of space, so I'll do it here. So this hemispherical shell, now we can, as we ignored the inside, we can ignore the outside. So we have the circle here, and we have this hemispherical top at the top, hemispherical part at the top here. And as I mentioned earlier, the force on some sheet of charge is going to be using the average of the two electric fields on either side, and we're going to use that here. So since we're only considering the top here, well, that doesn't really matter. The outside here, by shell theorem, is going to be, well, from here, the charge distribution was, there was a total charge of Q, so the electric field on the outside is going to be kq over r squared, and the electric field here is 0. So the force of repulsion here, since all this positive charge on the other side is going to be pushing it out, the force of repulsion is equal to, if we consider a small piece here, let's just give it some charge q. I already used that variable, but oh well. It's going to be q times kq over r squared, and it's going to be over 2r squared since we're taking the average. And from there, we can use a neat trick, and I think this actually appeared on an F equals ma problem, but you can actually think of all these pieces here and project it onto this surface, and instead give them, we'll give them the same magnitude, but now the area is going to be exactly smaller as the magnitude should be, because we actually only want to consider the vertical forces on this shell, since by symmetry the total force is going to be vertical. So total force F sub 2 is just going to be the same as putting all the charge, sorry, not putting all the charge, but projecting onto here. And well, that's going to be with the same charge density, that is. So the force is going to be found by putting the same charge density, which was q over 4 pi r squared, on the bottom here, and putting that as the substitute for q. And that might not be entirely obvious here, but this video is getting pretty long, so I'll just state that without proof here. And basically that means the total charge at the bottom here that we're simulating instead of using the real charge, because that gives extra components here, is going to be q over 4 pi r squared times the area here, which is 3/4 pi r squared. And so the pi r squareds cancel out, and it's, sorry, this is getting really slanted, and this is F sub 2 is equal to 3 over 16q times kq over r squared, and let's replace that with 1 over 4 pi epsilon naught, and so that gives us 3q squared over 16 times 4 and times 2r squared 4 pi epsilon naught. So this gives us F sub 2 is pushing outward with magnitude 3q squared over 128 pi epsilon naught r squared. So this part is a little bit hand wavy here at the moment, but it's actually correct. And so with that, we can combine what we found over here. F sub 1 is equal to negative 3q squared over 8 pi epsilon naught r squared, and this. And so we can get the total force, which I guess I'll continue down the actual page, is equal to F is equal to F sub 2 plus F sub 1, and this is negative, so this is equal to 3q squared over 128 pi epsilon naught r squared, and we want to subtract the attractive force of 3 over 8 pi epsilon naught r squared, which multiplying by, what is it, 16, is equal to minus 48 q squared over 128 pi epsilon naught r squared. So this is equal to negative 45 q squared over negative 45 q squared over 128 pi epsilon naught r squared, where the negative sign indicates attractive. And the fact that it's attractive can, I guess, be intuitively obvious here, because we had a higher charge distribution, higher concentration of charge at the center here, which is plus and minus, so that's going to be pulling harder. So now we're coming up to the last part. So we've solved the charge distribution, which was given here. electrostatic interaction force, which is given all over the place from here to there and back to here. And now we want to find the energy. So let me redraw our situation here. We have a uniform charge, uniform sphere with total charge Q, and then we have just this gap here with some positive charge at the top and some negative charge at the bottom. And so first thing we can realize is that the electrostatic energy is going to come with pulling of these two together and the pulling of the entire sphere together. And the reason you can see this is because electrostatic energy is just the energy required to assemble the whole situation. And after you assemble this inner part here, then the electric field outside it is 0, so assembling the outer part has no, there's no correlation here. But basically, let's first find the energy due to assembling this part. And the way we're going to do it is finding the integral over the total volume of epsilon naught over 2 times E squared dV. And so E squared is not negligible, but once you realize the total volume here is negligible, so this actually we can say is going to 0. And you can kind of check that a little bit more rigorously with yourself, by yourself. And so this is part C, let me just note that. So the only electrostatic energy is going to be due to assembling the outside total uniform charge Q. And the way we're going to do this is also with this value, this method, because I feel it's most straightforward for situations like this. So the integral we're going to be doing it over the volume is just going to be everything outside, since the electric field is 0 inside here. And the magnitude of E is just from shell theorem, Q over 4 pi epsilon naught r squared. Let's replace that with a little r so we can integrate over it, squared, to get E squared, of course. And we're going to integrate with shells surrounding this because it's spherical symmetric. And with that, the volume component dV is 4 pi r squared dV dr, and we're going to be doing this from r to infinity. And this is not that bad because we have a lot of stuff canceling. Let's cancel that epsilon naught over there, and it's q squared over, and let's cancel the 4 pi r squared, and it's going to be q squared over 4 pi epsilon naught. There's a 1/2 still here, and it's going from r to infinity, and we have r to the, we just have r squared because it canceled, dr. And so this is just basic single variable calculus, and that's going to be q squared over 8 pi epsilon naught r. And this is a pretty well-known result actually, since it's just the assembling of a uniform sphere, and that's the answer to part C. Answer to part B, and answer to part A, which is probably the most fundamental part of this problem, is actually discovering the charge distribution and applying uniqueness theorem. So that's the end of this video. I hope you enjoyed it. It went a lot longer than I expected, but yeah, subscribe to FODs and also my personal channel, Slipping Hexagons. Thank you.